Good afternoon, class. We are looking at pre-calculus practice test number 2, module 2, chapters 3 and 4. Here's chapter 4, exponential and logarithmic functions, part 2. We want to expand each log, which means we are going to follow the rules here. Log base 7 of x, y, z, we use the product rule. We use number 5, which means log of x plus log of y plus log of z, and all of them take the same base 7. There's really not much to it. ln of 9 over x, we follow number 6, the quotient rule. ln of the top, which is number 9, minus ln of the top, bottom, which is x. Log y to the power of 10, we're going to follow the last property known as the power rule. The power n becomes the coefficient, so 10 log y. Part D, we are going to use combinations here. First and foremost, we notice we have a fraction. So we are going to use the quotient rule. Log base x of the top minus log base x of the bottom. So that means log base x of a squared b to the power of 4 minus log base x of c to the power of 7. This one, we rewrite it as log base x of a squared plus log base x of b to the power of 4. Now this one, 2 sits in front, this one 4 sits in front, minus this one 7 sits in front. So it's very straightforward, everybody. And we are going to move on. All right, log square root of x cubed y to the power of 5. First and foremost, we can rewrite this as x cubed y to the power of 5 to the power of 1/2. So we are using all algebraic techniques that we know. So we can put the 1/2 in front. And then this one, we use the product rule, log of x cubed plus log of y to the power of 5. So we put the 1/2 in front. This is log of x cubed plus log of y to the power of 5. We get rid of the 3, we put it in front. We get rid of the 5, we put it in front. And now we multiply by 1/2. We get 3/2 log x plus 5/2 log y. So it's pretty straightforward, everybody. So what happens to ln of x over x squared plus y squared? We follow the quotient rule, ln of the top, ln x, minus ln of the bottom, ln of the parentheses, x squared plus y squared. And this can't be simplified. We are done. Any further. This is done, everybody. What about log base 4 of square root of x cube root of 10y z to the power of 10? By the way, with enough practice, you can do all of this in one shot, but we're going to take a few steps. So number 1, we are going to go with number 6, which is the quotient rule. That means log base 4 of the top minus log base 4 of the bottom. So log base 4 of square root of x cube root of 10y minus log base 4 of z to the power of 10. We are going to write this as 10y to the power of 1/3. We're going to bring the 10 in front. Now, we can separate this into log base 4 of x to the power of 1/2 and log base 4 of 10y to the power of 1/3. In each case, the exponent becomes the coefficient. So this became the coefficient here. The same thing, this becomes a coefficient. The same thing, this becomes a coefficient. So this one, 1/2 sits in front. This one, 1/3 sits in front. And this one is log 10 plus log y. So you have a 1/3 log base 4 of 10 plus log base 4 of y. So you distribute the 1/3. All right, so again, we are working with properties of logs. Very straightforward, everybody. So 1/2 sits in front. This one, 1/3 sits in front. Log 10 and log y, they're separate. And this one is already done. Now we want to go back to put it into a single log. So for example, this one, we are following this number 5, the product rule from right to left. So all you have to do, multiply these two, everybody. Multiply this by this. And it becomes log of 6x to the power of 9. So when you multiply 2x to the power of 4 by 3x to the power of 5. You see this. And part B, we are going to use number 6. And we're going to write ln of 6x to the power of 9 over x squared. And we simplify the fraction into 6x to the power of 7. So ln of 6x to the power of 7. Part C, you put the 2 here, you put the 3 here. So that means I'm using the power rule, everybody. First, reverse process. And now log of x squared plus log of x plus 1 cubed, I'm going to use the product rule and I'm going to go from right to left. So I'm going to multiply x squared by x plus 1 cubed, and I'm going to write log of x squared times x plus 1 quantity cubed. Now, in some instances, they may want you to actually multiply them out for full credit. So to me, it's not that big of a deal. As far as I'm concerned, this is done here. Okay, you don't have to multiply, but if they expect you to do so, then so be it. Now, what about this one? First, to put the 1/2 up here. And this one is log z cubed. And then you change the order. So this one and this one have a plus sign. So put them next to each other. So class, here's what we do. So 1/2 goes up here. And 3 goes up here. And we're going to put these two next to each other. So you see that in essence, if you just look at this part, that gives you log x z cubed. This one you change it to minus log square root of y. Now we use the quotient rule, reverse process from right to left. So log x z cubed over square root of y. We're going to solve equations involving exponentials, reminding everyone that if a to the power of x equals a to the power of y, then since they have the same base, they must have the same exponent. If a to the power of x and b to the power of x are the same, they must have the same base, a equals b. So in this case, they both have the same base 5. So they must have the same exponents. Remove the negative 4x, we make it positive. With negative x becomes 3x, divide by 3, and x becomes negative 1. And you can check it, of course. Now, the second case, part B, they don't have the same base. So notice we can write this one as 4 cubed, this one as 4 squared because the base is 4 here. So these two, we can add up their exponents. So 4 to the power of 3 plus 3x. And the right side, you don't have to do anything. Now, since they have the same base, namely 4, their exponents must be the same. So 3 plus 3x must be 2. Negative 1, x is negative 1 there. So it's very straightforward. 2 e to the power of 3x equals to 13. We are going to divide by 2. Now, either by definition or just take a natural log of both sides, the left side becomes 3x. So what is x? Divide both sides by 3. 1/3 of the right side. This is an exact answer, and you should always leave it as an exact answer, unless they ask you for an approximation. Then you can use a basic calculator to do that. E to the power of 2x minus e to the power of x minus 6 equal to 0. You have two choices. You can factor the way it is, or you can let this one be a variable of your choice. If this is, let's say, y, then this is y squared. And it's an easy factoring. You want two numbers, the product is negative 6, the sum is negative 1, y minus 3, y plus 2. Or just factor it with e to the power of x. It's your choice. Depends whether you feel comfortable with it or not. So either e to the power of x is 3 or negative 2. This one, you take the natural log, and x equals ln 3. And again, this is an exact answer, everybody, exact. And this one can't be because exponential functions can't be negative. Remember, for a basic exponential function, the range is from 0 to infinity. So it's pretty straightforward, everybody. We are going to move on. So we want to solve these equations, and the first one we just follow the definition. Log base 3 of 9k equals 2. We go with the arrow here. So 9k is 3 squared or 9. So k must be 1. For part H, first we use the product rule to put these two together. 4 times negative 5x makes it negative 20x. So log of negative 20x equals 2. And then we go by definition. Remember, when we don't have a base, the base is 10. Maybe I use a different color here. So the base is missing. That means the base is 10. So minus 20x is 10 squared, and that is 100. Divided by negative 20, x becomes negative 5. Please understand the argument of log can't be negative. So this has a number. We don't have to worry about it. When you put negative 5 here, makes it positive, and therefore it's okay. By that, I mean the argument. Now, about these two questions. So what we had here was a log on one side, number on the other. That means you have to bring all the logs to a single log and then go with the definition. But if you look at these cases, they have logs and nothing else, then just as with exponentials, if they have the same base, they must have the same argument. So in this case, notice log base 7, and because they have the same base, they must have the same argument. So 5n minus 2 and 8 minus 5n must be positive. You move things around. This becomes plus 5n. This becomes plus 2. 10n equals 10, n becomes 1. What about this one? Part J, when we have a bunch of logs, we make it into a single log on each side. Left side has one log, we are fine with that. But the right side doesn't, and we have to change it accordingly. So we put these two together using the product rule, and we go from right to left to make this log of 12x. So that's very straightforward, everybody. Now, they have the same base, namely, no base means base 10. They must have the same argument, x plus 12, and 12x must be the same. So what happens is we are going to move this one. This becomes 11x. Divide by 11, x becomes 12 over 11. Again, pretty straightforward, everybody. All right, let's see what happens here as we look at the left side. We notice we have a bunch of logs. Of course, the base is e. That's why we call it natural log. And on the right side, we have only one. So the right side, we don't have to do anything. We keep it. These two, we combine them using the quotient rule, ln of x plus 4 over x. That's the left side. The right side doesn't change because they have the same base, namely e. They must have the same argument. So x plus 4 over 4 and x plus 1 must be the same. We multiply these two, we get x plus 4. We multiply these two, we get x times x plus 1, which is x squared plus x. You don't have to move the x, we just cross it out from both sides. X squared is 4, x is plus minus 2. Now, we go back to original equation. If I choose minus 2 plus 4 is positive 2 is fine here, but it's not fine here. Negative 2 is out because this argument becomes negative. I don't even have to check with the next one. And that's the idea. You check when you have to. What happens here, now it's interesting. You have a bunch of logs on one side, number on the other side. The methodology is to put all the logs together. Even if we had some logs here, we would take it to the left and all the numbers together. So these two, we use the product rule and we write it log base 2 of x times x minus 1. And so x times x minus 1 is 2 to the power of 1. Obviously, this is 2, this is x. Let's write that. This is x squared minus x and equals to 2. We're going to move the 2 to the left. And we're going to factor. We want two numbers. The product is negative 2. The sum is negative 1. It's minus 2 and plus 1. So x either is 2 or negative 1. So there are two possibilities. Can we have both? And the answer is no. Why not? Let's find out. You have to check. If I put 2 here is fine. 2 minus 1 is 1, 2. If I put negative 1 here is not fine. I don't even have to check that. So negative 1 is out. I hope it's clear to everybody as to what's going on. Now we're going to continue with equations and solving where this equation 4 to the power of x plus 10 equals 3 is an exponential equation. We move the 10, that means we subtract from 3 and we get -7. And as you remember, exponential functions, the range is always from 0 to infinity. That means there is no solution here. What about this one? One easy way is to recognize 1 is any base you want it to be with the exponent 0. So 1 is 5 to the power of 0, 2 to the power of 0, 10 to the power of 0. And because the base here is 7, it's 7 to the power of 0. That would be the choice. So x minus 10 must be the exponent 0, which means x must be 10. So that's pretty straightforward. Part C is as difficult as it gets because we want to come up with the same base. There is no way to come up with the same base. We want to come up with the same exponent. There's no way to do that. So the methodology is what? When you want to solve for the exponent x, then you have to take a log, either natural log or common log, makes no difference. So if I take the natural log of both sides, what happens is the exponent sits in front. So this becomes x ln 4, this becomes x minus 2 times ln 9. And it's important to know that ln 9 is just a number, everybody. Okay? ln 9 is just a number. The difference is when you keep it as ln 4 and ln 9, those are exact numbers, okay? Those are exact numbers. So what do we do? Well, on the right side, ln 9 is a number distribute. You get x times ln 9 minus 2 ln 9. We want to come up with the exact answer. We don't want to use the calculator. And to do so, because we are solving for x, we are going to move this one this way. As you move this one this way, you get minus x ln 9. And now on the left-hand side, you see x is in common. You can take it out. Divide both sides by ln 4 minus ln 9. And what I want to show you right here, if you move things differently, okay, then you could get, if I put this negative at top or at the bottom, makes no difference. You could get 2 ln 9 over ln 9 minus ln 4. Please understand how I came up with that. I want to make sure that we just erase the this part so you can see what I'm talking about. If you apply this negative to the numerator, you get minus 2 ln 9. If you apply to the denominator, you get minus ln 4 plus ln 9. Okay, so plus ln 9 minus ln. So they all mean the same thing. Also, if in the beginning, instead of natural log, we used log, that means common log. This would be a common log, this would be a common log, this would be a common log, and that's important for everybody to understand, okay? What I did, I used the least number of moving, otherwise uh, makes no difference. Assume log base b of 2 is a, log 3 base b is b, log 5 base b is c, and we want to evaluate those accordingly. That means you have to cut them into factored format such that they involve 2, 3, and 5 and nothing else. You may recognize this as 2 times 25, which is 5 squared. And now we are going to use number 5 and number 7. By now we know how to break this into pieces. So this is log 2 base b, and this is log 5 squared base b. And this one, we can put the 2 in front, everybody. Now log 2, we replace it with a, 5 with c, we get a plus 2c. Very straightforward, everybody. Well, about 300, we have to do the same thing. So what is 300 equal to? I hope you are comfortable with factoring. 300, please understand, each 0 means 2 times 5. So that means 3 times 2 times 5 times 2 times 5, which means 2 squared times 3 times 5 squared. Now let's write this as 300 to the power of 1/5. Put the 1/5 in front. And cut the 300 by factoring. And I'm going to quickly show you the second method of factoring. This is simple enough that we should be able to do it in our head, as I've mentioned it here. But just in case, I want to show you how to factor this, okay? The method that you should have seen in algebra. And here's what you get. So we would put 300, and then remember prime numbers are 2, 3, 5, 7, 11, 13, and you continue. So you start with 2, you get 150. 2, you get 75. Can you divide by 2 anymore? No. So go to 3, 25. Can you divide by 3 anymore? No. 5. You get 5. 5, you get 1. And you get to 1, you're done. And this means this. Okay, everybody? So I hope everybody is okay with that. So this is very straightforward. Now you cut this into pieces, meaning this one is log of 2 squared, log of 3, log of 5 squared base b, and log of 2 squared is 2 log 2. This is log 3, this is 2 log 5, all of them same base b. So let me erase again my work. This one is log of 2 squared or 2 log 2. This one is log of 3 with the plus sign. This is 2 log 5, and all of them take the same base. You're not changing the base. And now you plug in. So you get 1/5 of 2 times A plus B plus 2 times C. That's how you do that, everybody. A nuclear reactor contains 200 grams of radioactive plutonium, P239. Plutonium decays according to the formula equals A sub 0 e to the power of negative 0.00000284 T. How much will remain after 5,000? And I'm going to remind you that n of t is n sub 0 e to the power minus kt. That's for the exponential decay, such as radioactive substances. For this, you recognize that A sub, so this is the formula that is given. This is your A sub 0. So 200 represents A sub 0, and T is 5,000. So first, we are going to write this. That's extremely important to notice that. And now into this formula, we put A sub 0 is 200 and T is 5,000. Now you put that into a calculator. The product of these two, negative 0.142, raise e to that power multiplied by 200. And whatever you get is the same units, grams, 173.52 grams, everybody. So what it means is that after 5,000 years out of 200, 173.52 grams would be left. Find the half-life. When we say half-life, it goes to half of its original size. So you change the A to A sub 0. That's the meaning of half-life. replace a sub 0, a with half of a sub 0. So we drop a sub 0 from both sides. We take a natural log of both sides. And you take the natural log of the left side, it's just ln1 minus ln2 or minus ln2 or just ln of 1/2. When you take the natural log of the right side, ln of e to some power, it just gives you the exponent. So what is t? Is the left side divided by this number. Remember, ln1 is 0, everybody. And you can drop the negative or keep it, it doesn't matter, they will cancel each other. So minus ln2 over minus 0.0000284. The negative signs cancel out. You do the math here, put it into a calculator with a bunch of decimals, and you get 24,406 years, 0.59. Now, it's important to know this is an approximation. Sometimes they may just round it to the nearest ones or even tens, whatever they ask you. If they don't, you have to keep it with many decimals.